Good morning, friends. It's Ben again, and this is a video for the differential equations class. The topic it's on is separable differential equations. And let me share screen real quick here and show you the essential notion for a separable differential equation is that you're going to be able to find some way to rewrite it so that it's of the form dy dx equals some function of x times some function of y. So if you had just plain f of x, like an x squared, times some g of y, like y minus 1, then that would be fine. But if it said x squared plus y minus 1, there wouldn't be a way to factor it like that. So once you have something like that factored, and then you're going to be able to divide and integrate both sides. The reason we refer to this as separable is both because you can separate the f of x and the g of y, but also that we, as a formal manipulation, think about taking dy and dx and separating them into two pieces. Technically, there is a bunch of stuff that's hidden there in doing that. Now, the one thing that we have as some difficulty there is integration. So if the integral that comes up is something you know how to integrate, then you're on easy street. But if it turns out to be something you don't know how to integrate, then it's rough. I think I need to go ahead and try to make a review of the tough integration techniques, some videos about that. But that is the reason why Calc 2 is a prerequisite for this course, because you need to have gone through all of those hard integration techniques before you get here. So, all right, with regard to that, I want us to look at something here. So this is an example of something that we could get as an initial value problem that is a separable differential equation. As you'll see there, that y would divide out, and this can turn into dy over y. And then I'm going to leave the 0.6 over here and put the dx with it. And you could move the 0.6 with the y, but there's going to be something that will make the manipulation a little bit easier if you leave it over there. So, of course, on the left-hand side, you get the log of the absolute value of y. And then on the right-hand side, you'll get 0.6x and then plus c. Please note that you do technically get a C1 on the left and a C2 on the right, but they may be different C's, and so I always just put 1 on one side, and it is technically the difference between the two. So once I get to there, I want to go ahead and exponentiate, and I'll have the absolute value of y. It's going to be equal to e to the 0.6x plus c. Notice the plus c is up in the exponent. And so the thing that I will do with that is to turn this into e to the 0.6x. And then it's times e to the c. And so that is going to be some other constant. And if you just really want to, you can go solve for your c and keep it in the exponent, but it doesn't really serve any purpose, okay? Now, then a tricky bit here is I always go ahead and just work with y equals at this point, okay? The reason that it's a little bit tricky is that if you had an initial condition up here, where the y of 0 was set equal to a negative number, then just dropping the absolute values kind of doesn't make entirely a lot of sense. But recognizing that that k could now have been a negative e to the c instead of a positive e to the c kind of takes a multitude of sins and fixes them all. So then when you plug in and say that y of 0 needs to be equal to just k e to the 0, so just k, then that says that the 15 goes here. And so your y of x that we're getting is 15 e to the 0.6 x, all right? So this kind of problem actually shows up as a bacterial or other population growth in the presence of unlimited resources. And so this is actually a kind of an applied problem, you know. In that case, generally the variable we're thinking about is going to be t for time instead of an x here, but we can also have things that have that kind of thing going on. You'll find this sort of thing also shows up in other applications where there's exponential growth, such as half-life problems, okay? And then those half-life problems can be applied both to carbon dating sort of things, but also to heat type things. We'll do an example here in a second of that. Actually, maybe we'll do the next example as that, all right? So sharing screen again here. So in this example, what we've got is our dy dt is equal to k times e minus y. So here we are thinking about the value of y being a temperature, wow, can't write, for some object. And the reason I did not use a t for that is that generally we use the little t for time. And when I start saying dt, it's kind of hard to follow. But in any case, this is the temperature of some object. And then here we have the temp of the environment. And so if you have an object that is hotter than its environment, you expect for that object to cool down. And if it's cooler than its environment, you expect for it to heat up, okay? So I have a little graph over here to the right with just this sketch. If you put the line of y equals e here, and we think about that things heating up will come up from below, then that means that the derivative needs to be positive. So we would go over here and think in this equation, if I want dy dx to be positive, then since e minus y, since y is less than the value of e, then e minus y is going to be positive. So I'd also expect for my k to be positive. Similarly, if we've got a value of something where the y is more, then e minus y would be negative, and we would expect for the k to be positive, so that when you multiplied it by the 2, you would get a negative there as well. So we get the kind of behavior we expect out of this. And this thing here of y equals e is what's referred to as an equilibrium solution. If you had y equals e as just a constant solution, then you would find that dy dt needed to be 0, and also that e minus y is 0. And so that would mean that it would actually satisfy the equation, okay? But insofar as solving this here, we can then put dy over e minus y, and that's just by dividing. And then over here on the right, we'll have k times dt, and we're going to integrate both of those. The one on the left would be log of the absolute value of e minus y, and the one on the right would be kt and then plus c, okay? And then when you exponentiate, you'll have your absolute value e minus y is equal to, and then I'll have an e to the kt here. And I don't want to use another k sitting out front, so I'm going to use, I don't know, I guess an a here temporarily. And we could, at this point, actually drop the absolute values with the understanding that we will need to have the sign of a match whatever the sign of e minus y is, okay? And so then you can subtract and divide by negative and have that your y needs to be equal to e minus a e to the kt. And then because y of 0 needs to be equal to e minus a, and that needs to be equal to the initial temperature of your object, then the a needs to be equal to e minus y naught. And so we end up with a y of t here being e minus quantity e minus y naught e to the kt. Okay. In practice, when you're actually doing the problem, you will end up having another condition, so that it in effect ends up giving you a boundary condition or a boundary value problem. And you would plug that back in to figure out what the k is. And and the e would have to be something that's actually given to you in the problem. So, all right, so that again was something where the integration wasn't super challenging on it, but it was something where we had to do a little bit of tweaking around to get everything to work. All right. So the next sort of thing to look at is something that again has an application to populations, and that is looking at the logistic model. So whereas our model for unlimited exponential growth with unlimited resources really had our derivative, our dy dt, being equal to some constant times the y. That meant that you had your derivative being proportional to that value that you wanted there. So here we are going to look at something that is a little bit of an expansion of that. Okay, so here we're going to think about our population P, and we're going to have this, this R times P and then K minus P. So you can do this in a little more of a way that makes all of the variables appear more clearly for your application, but this is really the easiest way to do it from the math end of things. So if you have this sort of idea going on, the R that we have there is going to play the same kind of role as the proportionality constant did in the previous problem where we were talking about exponential growth. But now, in addition to being proportional to P, it's jointly proportional to that and K minus P, where K is something that we use to represent a carrying capacity, some maximum amount that we might have for a population. So if you've got something like that going on, then you have an equation that just falls into this sort of format. And if I took values for P that were equal to K or to 0, either one of those solutions is going to be a constant solution and have a derivative of 0, and therefore when you plug it in and get 0 on both sides, it satisfies the equation. But if you choose an initial value that is larger than your K value, your carrying capacity, then R and P need to be positive, but K minus P will end up being negative. And that means that you're going to have negative growth, which means it gets smaller. It goes toward that value of k. If you have a negative value for your p naught, then that means that both the p and, that means that the p is going to be negative, but that the k minus p, because it will be adding something onto k, is going to be positive. And if r is positive, then all those are negatives, and that means things get pushed away if they start in this negative regime down there. But anything that is in between those, you will end up having the p-value be positive, but k minus p, I'm sorry, said the wrong thing. P is going to be positive and k minus p will be positive. So that means that you're going to have a positive growth rate, and that's when you have things going upward. So the shape of the curve ends up being kind of an S shape. So, and it has that p equals k then as an asymptote. But doing the actual solving of it, we would write down here and do dp as our first bit, and we're going to divide by p and k minus p. And over on the other side, we'll have r dt. And then we're going to integrate. And I think everybody's going to be able to do the stuff over here on the right-hand side. The part on the left-hand side is the hard part. And what you have to do for that is to think of this 1 over p times k minus p, and you set that to be equal to something over p plus something over k minus p. And this again is a trick from Calc 2. We refer to the Heaviside cover-up method. And what that means is that you pick something like the p over here, and you say that it would be a bad idea to have that be 0. So when I make it 0, I will cover up the p that's over here and plug in p equals 0, and then I will have 1 over k, right? And so then I'm going to just make a quick change here, and my a turns into 1 over k. And then the same sort of thing for my b. I think about k minus p, having k equal to p is a bad idea. So cover that up over here. And when I plug in k equals p, I don't pay attention to that part. And then I also get 1 over k. And so then this bit here turns into 1 over k as well, right? And so now I'm able to integrate 1 over k times 1 over p and plus 1 over k minus p dp, and that will be 1 over k log absolute value p minus log absolute value k minus p, and that then would be equal to 1 over k log absolute p over k minus p. Okay, and then if you'd like to, you could also take this part here out and think about a kth root or something. But it's probably easier, since this is all supposed to be equal to RT plus C, to go ahead and multiply both sides by the k, have the log the absolute value p over k minus p is equal to k RT plus, now I should write kc, but I don't have a value assigned for c yet, so I'm going to just not worry about it, okay? And it'll be some c there. Then when I exponentiate both sides, we'll have p over k minus p, and that will be equal to something times e to the KRT. Okay. And then we have the matter of trying to solve for P, which is a little bit of a headache, but you multiply, you cross multiply on both sides, pardon me, and then you'd have P times K e to the, oh, sorry. I meant to have that say equal to K A e to the RT, and then minus P times A e to the RT. And then you can add stuff to both sides and divide out and have that your P needs to be equal to K A e to the RT divided by 1 minus A e to the RT. And if you would like on that, then you can do some further simplification there. But notice that we need P of 0 to be equal to P naught, and that R and K are something that are inherent to the problem. So we're going to want to think about, we can think about this at two different places here. I think I want to solve for my, P naught equals KA over 1 minus A. And therefore we've got to solve for the A. And because the video is running a little bit long, I'm actually going to beg off on that. But you should be using the same technique as we did previously there. It's just that now your expression for A is going to be kind of a mess. And you may want to try to write things a little bit simpler by getting rid of compound fractions and such as that. Okay. All right, so that does us some fairly straightforward examples of separable differential equations. Now it's your turn. So look at these examples of separable differential equations I've asked you to do for the day, and try to get those in a form that I can read them pretty well as quick as you can. I've forgotten what the due date is, but all right. So otherwise, I'll let you all get to things.